So the neural networks as such are inspired from neurons in the brain, and we will not go into too much of the biological stuff here, but I will give a mathematical formulation, and then again based on that itself I will try to say why it's a neural network. So the neural network or the perceptron, when it was first proposed, is a network which is usually visualized like this. So I have these inputs, and then I have some operations, and then I have some way to check the threshold of the output, and then I have the final output. So these are the inputs, so we can number these inputs as x1, x2, x3 and xn. Okay. So this is a multidimensional input, and these nodes are connected here by, let's say, w1 weight, okay, and then I have these nodes w2 weights and so on, okay, wn weights and so on. So all these are connected. So this is a pictorial representation of the neural network, but we can also try to understand what this graph means. Okay, so this graph essentially means is that the x1 component gets multiplied with w1. So this is what the sum operation means. Okay, sum operation says that you take a linear combination of these with the respective weights. So in this case, if we take the linear combination with respective weights, then we have x1 w1 plus x2 w2 xn wn. Okay, so that's what this this block means. And then later on we have some activation function, it's usually called. So this is called activation. So basically it's nothing but one function composition. Okay, so I can say that this and then multiplied with some not multiplied but composed with some activation function. Okay, so this is what will be the output after this. Okay, so this is what a single perceptron means. We take a linear combination of the input and then we do some activation. Now this activation can happen in many ways. So there are activations like threshold functions. There are activations like sigmoid. Sigmoid we have seen a couple of times, and there are activation functions like ReLU, rectified linear units, and then we have like tan h, tan hyperbolic h, and so on. Okay, so these are activation functions. Depending on the architecture or the problem at hand, we use one of these. Okay, so now yeah, so this could represent a machine learning problem basically, and this is the parameterized function that we have, and this is parameterized by the weights w1 to wn. Okay, so for example, this could be let's say a prediction based on some features. So these guys are called features. Okay, so these guys are called features, and this output is called labels. So we have features, we have and label, and in machine learning problem, given a set of features, we want to predict the corresponding labels. Okay, so we can have one example on this. So if we look at an example, so one of the common example is, let's say, housing price prediction. Okay, so this is housing price prediction. So basically here it means that I'm supposed to predict price of a house. So let us say I go and look for data and I see a lot of houses. Obviously not all houses are the same type, so there are variety in houses, and depending on the variety, location and many things, the prices of the house can change. So we can have some samples where let us say I have, so let us say some of the features could be number of bedrooms, okay, number of toilets, number of balcony, okay, size of the house, okay, location, okay. So location may not be easy to encode, okay. So we can have these features of the house, and maybe the size of the this would be the size of the house, and then you can have size of the garden if there is a garden. Okay, if it's a flat, then it's not. So, and then based on all this, you have let us say a price prediction of these houses. Okay, so then we can have features which will denote one row of this. So let us say the first house will have its own features. So let us say this first house has 1 bedroom, 1 toilet, okay, balcony is 1, size of the house is, let us say, 200 okay, feet, let us say 200 square feet, and then size of the garden is just 50 square feet, and the price is let us say the price of this house is let us say 10 lakh, okay, rupees, let's say. And then so prices, we can put this in or let us say in million rupees, okay. So this is let us say 1 million. So we can have features again for the different house. So this is for the first house. Then the second house could have features like 2 toilets, 1 balcony, size is let us say 800 meter square, balcony size is 60, and this is let us say 3 million rupees. Okay, so this way we can have features. So this input that we have here, that corresponds to one row of that table. Okay, so hence we can denote this as the whole vector, we can denote this as superscript 1. Okay, so then I can denote this as superscript 1, this is the first row, superscript 2, this is the second row, and xn, this is the let us say nth row. Let us say I have data for n houses, then xn is the nth row of this. So these are called this is level data, obviously. So this is the whole thing. If I take them, then it will be a matrix. Okay, so I can put this data x1 whole row, and then x2 whole row, and dot 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 xn whole row. That becomes my one big matrix, capital X. And then based on this, I'm trying to predict the output. So this is y1, y2, yn. Okay, so y1, y2, yn are the prices of the corresponding houses. So this mapping that we are trying to learn is, given this x, what could be the function f, okay, that will kind of predict this. Okay, so next time a new sample will come. Okay, so let us say a new sample is come whose data is not there, and we are supposed to kind of, once we have learned this, we have learned this, meaning that we have learned the theta. Here theta refers to the weight matrices here, w1, w2. So here we can say that theta refers to w1, w2, wn. Okay, so combined I write this as theta. So this is our parameter in our model. So based on this data, we build a loss function, right? So loss function will be the simplest one would be this minus this. Okay, let us say. Okay, depending on, so in this case we can take an L2 loss. So this is our, so this, let us say for the first sample. Okay, and based on this the output is y1, right? So this way we can build a loss function. So let us say loss on the first data is L1 is f of w1 x1 w1 x11 plus w2 x12 and so on, and wn x1n. Okay, and this minus the predicted price of the house, and this is the loss we can take, and we can take a L2 loss, meaning we square this. Okay, so this is loss function for sample 1, and then we can also build a loss function, loss that we incurred for sample 2. So f w2 x21 plus f w2 x22 plus dot 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 wn x2n and minus y2. So this is the loss we have for for sample 2, and this way we can build loss for all the samples, and then we can sum the loss, and the global loss we can define it as L, and this is for the theta. Theta, remember that it collects all the weights, and then this is for the whole matrix X, and this could be, and it also for the levels Y. So let me write it again. So we can build a total loss which is theta, and then X, Y, and this is sum of the losses made on these samples. So this is theta, X, I, and let us say this is I, and YI. Okay, so the ith Y subscript, we are using subscript Y. You could have used superscript Y also, because Y will be just a number here. So we are taking subscript. So Y equals 1 to total number of samples we have. Okay. So using this small losses, we created a big loss function, and then it is an optimization problem basically. So what we are asking is, what is the value of theta for which this loss is minimized? Okay. So this way, we learned a good theta for which we can do the predictions of X matrix to Y matrix. So once we solve this optimization problem, minimize this loss, meaning this is very well predicted, predicting the levels. When we minimize, that's what this will mean. And once we do that, then we get an optimal, let us say, value of this optimization problem, which is f theta theta star. Okay. So if I have to, so if we go and solve this optimization problem, so we will go and solve this optimization problem, then this will be minimize L theta xy, and this is minimization over theta. X and y are fixed because during training X is given, Y is given, so there is nothing to do with X and Y. They are just part of the loss function, but the variable here is theta. Theta is something you're supposed to tune, and you minimize this. So let us say you use something called a gradient descent or stochastic gradient descent. So you can watch the video to learn about this algorithm in optimization for machine learning. That's also in my YouTube channel. So there you can go and check how these optimization methods are employed for machine learning problems. So let us say I minimize this, and let us say I do argmin, and what I get is theta star. And so theta star is the value for which I get the minima. Then my function has learned, and then in that case I can start doing the prediction with f taking the optimal. So let us say theta star will be w star and so on, right? So then in that case f theta star, where this will become my prediction function, and this will be with, and this will take a value x. Now x becomes a variable during prediction because new sample will come, and then I'm supposed to predict. So in that case, now x becomes a variable, and then so basically x one, let us say the test data is denoted by t, superscript t, let us say this test data, then first component of test data, and then I have w star, basically w star first component plus xt2 w star second component plus xtn w star n component. So this becomes my prediction function now. W star are known here. So because theta star, which is in our notation, theta star is w star 1, w star 2, and w star n is known. So since this is known, now it becomes a prediction function. Okay. So since it becomes a prediction function, then we can start predicting. So when a new test data comes, then we apply this f theta star on new test data, and then we whatever is predicted by f theta star, we take it as a predicted output. So this is basically machine learning via some neural networks. In this case, I have shown just one perceptron. Basically, this is just one perceptron, and all the calculations involved with this one perceptron. But the idea could be generalized, and it could be made into multiple of these perceptrons combined. Okay, so we can combine many of these in as hidden units, and then layers, and so on, and and make it really deep, let's say. Okay, so hence the people study so-called deep neural networks. Basically, it's a combination of these over many layers and many units and so on. Okay, so this is the basic idea of. So now, as I said, we can make this into a deep neural network, and we will try to extend these ideas now. So what we will do is that now we will make it into a multi-layered multi-layer network. So it's a multi-layered network. In this case, now I will have input units, and then I will have hidden units. And then there are our connections. So we will consider a fully connected network, so meaning all nodes are connected to all other nodes. So each input unit is connected to each other, and so on. So basically all connections are possible, and so on. Okay. Similarly, this node gets connected to this connected to this, and similarly this gets connected to this, and so on. So you get the idea basically. So we will connect each node with the forward node. Okay. So and only node from the previous layer. So we call this layer. So this is like layer 1, this is layer 2, this is layer 3. You can also say this is layer, let me check the notations I use. So we can also say the first layer as starting from 1. So let us say this is 1, this is 2, this is 3, this is 4, this is Ln. Let us say we have n layer. Okay. So layer 1, it be the input layer basically, because it has nothing to do, it's just the input data. And then we have an output like this, and this we have output layer. Okay, so here we have the outputs like this. And so this is our output layer, and this is our input layer, and we have all the connections between them. And this gives us the input layer and then the corresponding connection the output layer. As I said, each node or sometimes it's called units. Okay, so each of these node corresponds to one of these perceptron. Okay, so we call this perceptron. So one perceptron is this. Now we leave the input layer, but these guys are the perceptrons, and as you can see, they are connected by so many of these perceptrons. They don't have any connections between the hidden units between the same layer. So I don't put any edge between this and this and this. Okay, it's only with the next one. Okay, also you are not at least in the classical case, you are not allowed to put an edge from here to here, although there is a concept of skip connections and so on. But for the moment we don't assume that. We say that the units from the current layer can only connect to a unit from the previous layer, and we say that it's fully connected, so meaning any unit from the current layer is connected to all other units from the next layer. Okay, so that's called multi-layered. It's multi-layered because there are many layers now, and there is an input layer, there is an output layer, and these layers which are between input and output layer are called hidden layers. Okay, because they are between input and output, and these units, each perceptron are called units, so we call this hidden units. Okay, so this is hidden unit at layer 2, these are hidden units at layer 3, and so on. Okay, so this is the generic description of a multi-layered network, and if the layers are many, then we call it a deep neural network. Okay, so if the layers are many, layers, then it's called deep neural network. Okay, if there are many layers, then we call it deep neural network, and any learning procedure using these neural network is called deep learning, and learning using deep neural network is called deep learning. Okay, so these are the terminologies that you should be aware of. That's what hidden layer mean, hidden unit means. So these will be used again and again. And each of these hidden units are essentially, as I said, perceptron. So they include a linear combination. So you can see here there were two steps involved. The first step was linear combination, and the second step was activation. So these two things define a perceptron. Usually you also have a bias, okay, which is the B term, B bias here. So usually we add one more weight, which we call it B. So this is also part of the unknown. Okay, so we can put this B also in the theta that we want to learn. Okay, so this is a full description of a perceptron, and then using this perceptron I can build a deep neural network, and then I can use this to learn complicated tasks, because now looking at this we see that there are so many perceptrons and so on, so the expressivity of these networks should be very good, and which is indeed what is observed in practice. Deeper networks, okay, larger networks usually have a lot more expression power, and it can be used for, let us say, complicated tasks of speech synthesis or video synthesis and things like that. So this is the basis of the modern day revolution in machine learning. There is a part where I said we build a loss function. So similarly here we build a loss function. It's just that it will be a little bit complicated. There will be a lot of function composition going on here. Okay, so this function composed with this linear combinations, and then activation for this. So linear combination will be all the edges that are coming from here. So this linear combination with these weights, and then you do the activation, and then there is output going out. Okay, similarly here you do the same thing, linear combination of all the edges that are coming there, and then activation, and then you get the output. So this way you keep doing this. Depending on the type of problem you have in hand, so if it's a binary classification, then you're supposed to prove to show output which is 0 or 1. So 1 means that something is there, or 0 means something is not there. But if it's a multi-class classification problem, then we use something called softmax. And then if there are k classes, then the softmax will produce a vector of k, and it gives me a probability of each of the components. So the first component is horse, and if it says 0.7, then it means like the input image has 70% probability that it's a horse. Okay, so that way we can also extend this for multi-class classification problem, and of course also for regression problem. So this is the basic intro behind the deep neural networks. Now, so if we talk about the loss functions, then as I said, loss functions depends on what I'm supposed to do. So if it's a regression problem, then I will take the usual L2 loss. So let us discuss briefly about loss functions. So loss functions could be defined as L theta equals 1 over t, and then let us say divergence or small l that I'm using. So let us say this is like small l, and f of x xi, and then w, and then the corresponding output yi. So this is something I have described before as well. So let us say number of samples are n. So this is how the loss function I have defined as well previously. And here the f function that I have written here, now I write this as xi comma w, meaning this f does this linear combination first inside. Okay, so now I have to replace this f by a generic f that does the linear combination and then applies the activation as well. Okay, so we can take that as a loss, and so here the f xi w is redefined as taking some activation function f on if this is making issue, we can also take it this as a g, let's say. Okay, otherwise it might create an issue with our previous notation. So this is like g xi w is f of dot product of xi with w and plus the bias as well. Okay, so bias goes with let us say sample 1, basically sample. There is no sample for the bias. If you come and see here, then there is no input essentially for going for, there is no linear combination of these. So b is the weight here, but then we can take this as 1. So 1 times b, so there would be a b going in there as well. So hence we write this this B separately. So this becomes our loss function, and then as I said, here itself we have now various possibilities for defining the loss. So one of the possible loss could be L theta could be half of norm of, yeah, so we can define this as half of the output. Let us say if the output is characterized by a vector, then in that case I can call this as yeah, I can call this whole thing as let us say this is the loss between so let us say we call this so let us say we define this as some Z, and Z, or what should I use, P, let us say, and P is these values that we have. So P is defined to be, let us say, P1, P2, Pn, okay, and capital Y defines Y1, Y2, Yn. So then where Pi's we define it to be these G of xiw, where Pi is G of xiw. Okay, so for each sample we have this Pi, so xi and then wi, we do a linear combination and then activation for that. So we can also use bi, we change the bias each time. Okay, so this with this vectorized notations, we can now write the loss as norm of p minus y basically. Okay, so we can write the loss as norm of L2 norm of p minus y. Okay, if it's a regression problem, then we usually will take L2 loss, so p minus y. So if we continue from there, then we have p, we have defined it in a vector form, and then we have the output y being defined. So we can define the L theta loss as now half of norm of taking L2 norm between two vectors. So in this case we have p minus y squared. Okay, so this is one possible loss function. But then if we have let us say a classification problem, then we can define different type of losses. So for binary outputs, so in binary outputs we mean that y belongs to either 0 or 1. Okay, so for binary outputs we have the so for binary output from our notation that we have these pi's. For binary output, then p will be just 1. Okay, eventually p will be just one output will be p1, let's say, and then this p1 will be either 0 or 1, and then we compare with y1 which is either 0 or 1. Okay, so since p is coming from last activation, let us say sigmoid, then it will be some probability value between 0 and 1. Okay, so in the binary output we have only one output, say small p, and in this case, so in binary output what will happen is that regardless of however big this neural network I have, eventually what I'm supposed to do is to predict one single value. So in my final output layer that we will have in my deep network is that eventually everything should be going to 1, because it's binary output, so output should be eventually just 1. So depending on what I choose, so let us say usually I will choose sigmoid for binary, then sigmoid gives me a value between 0 and 1. Okay, so this value that I get, let us say this is p, and this will be between 0 and 1. And from the data that I have for a given input, I will have the known output data, which is let us say y, and this will be this will be either 0 or 1. Okay, so let us say I throw in a cat image, I make it's a 2 by 2 pixel matrix, and let us say grayscale, this is a matrix, and then I make this into a vector, and then I pass this vector through this complicated linear combination and activations, and eventually my network will predict whether there is a cat or not. So if there is a cat, then it will predict 1, but the problem is that this is sigmoid, so it may not exactly predict 1, but it may predict something like 0.9, okay, or it may predict something like 0.02, something like that. So then I have to kind of interpret, because this will be like a probability value, so I have to interpret that, okay, after the output I have its sigmoid is predicting 0.9, and then I have to say, okay, it's very likely a cat, and hence I'm going to predict a cat. Okay, so in a binary classification case, we have one output, and this output is a probability value because its output is coming from the sigmoid activation function. So sigmoid is 1 divided by so sigmoid function f sigmoid is of x is 1 divided by e to the minus x. So this function basically 1 divided by 1 plus, yeah, so this is sigmoid function. So basically you can say that it is between 0 and 1, so it will give you some kind of probability value. So we have in the binary classification only one output, and these are probability values between 0 and 1, and the labels for the binary output, the labels, let us say, are y, and they are between 0 and 1. Okay, so the labels are between 0 and 1. Labels are 0 or 1, and the probability values, the output that we produce is between between the interval 0 and 1. So with this we can now build a loss function basically for this. So in this case the loss function we can define it to be something called cross entropy loss. So this will be L of computed between P and Y, and this will be minus Y log P minus 1 minus Y log of 1 minus P. Okay, so this is called cross entropy loss. This is used for binary classification, cross entropy loss. Okay, so so obviously, if let us say if the we can also see this as kind of expected log loss basically. So because here we are kind of computing expectation of the log of the probability values. Okay, so the or negative of the negative negative of the expected. Okay, we can see this like that because it's log of p, and then we are we may take a expectation about that, right? So here if we see if the level was 1, then this term remains, and then if our prediction is close to 1, then this is indeed close to 0. Okay, but if the level was 1, then this term goes away. Okay, so similarly, if level is 0, the output is not a cat, let's say, then this becomes 1, and then here if it is p should be close to 0 in that case, because it has to match y equals to 0, and if that is the case, then again the loss is 0. Okay, so we can also interpret it like that. Okay, so it works for both 1 or if the prediction is 0, and it intuitively does make sense that if my prediction is good, then this loss will be, if y is 1 and then my prediction of p is close to 1, then overall this is close to 0. Now based on this, if I based on this, now I may and so this is my loss function, and then again I can minimize this loss function. So remember that p that we have, p is coming from the g, and inside g we have the weights w. So those weights are the parameters of my network. Okay, so overall we can also write p as sub of theta basically, because this is parameterized by theta, where theta is collection of the weights. So we can also say that this is p of theta, and here we can say that this is p of theta, where theta are, in this case, are the w weights. So this is again yeah, it's a parameterized model. So then if I have to compute a good theta for binary classification problem, then again I'm supposed to minimize this this loss p theta y over theta. Okay, so for binary classification problem where I'm predicting 0 or 1, then usually we take this kind of loss. Okay. Now this type of loss could be generalized also for multi-class classification problem. So in a multi-class classification problem, let us say I'm predicting um, out of multiple objects. Okay. So if an image goes in, then the object is not just about whether there is a cat or not, but it could be that in the image there are cat, there could be dog, there could be horse, and so on. Okay. So in that case, we can also extend these ideas, and rather than putting, since it's a multi-class classification problem, we may have to kind of now introduce multiple nodes from the output. Okay. So then this, in this case, let us say there are k classes, so there will be k nodes as an output. Okay. So in this case, our output y will be a vector. Okay. So in this case, our y will be, let us say this is y1 class, y2 class, y3 class, y4 class, and this y will be y1, y2, y3, y4. So this is still a classification problem, but not binary, but it's a multi-class classification problem. The number of classes are 4. Okay, the k is 4 here. So the predictions that we will do, which is the vector p that we will produce, it should also produce, let us say, 4 outputs. Okay. So this is what is kind of the given level, and what we will produce will be p1, we will produce p2 here, we will produce p3 here, produce p4 here. Okay. So our predictions will be p1, p2, p3, p4, let's say, and the actual level for these data would be y1, y2, y3, y4. Okay. So if it is a classification problem, so let us say I create one example here. So let us say an example would be, the output would be, let us say, cat, dog, deer. So let us say this is the possible classes I am looking for, and then cat is at number 1 position. Okay. So if my image really had a cat, then the output, the ideal output would be 1, 0, 0, 0. Okay. So basically with 100% probability, I have 1 at the cat position and then 0, 0 elsewhere. Okay. And then I will run the network with the weights that I have initially, which will be may not be very good one initially. So it will do some predictions. So it will give me some predictions for p1, p2, p3, p4, which, as I said, will be random initially because the network has not learned. So it will give me some arbitrary values. But then I will compare with the actual value and this arbitrary value, and then do the optimization and then let the network learn. So here one of the question is, how do I produce this p1, p2, p3, p4? Okay. In binary case, I used a sigmoid, and sigmoid gives me values between 0 and 1. Okay. And then after that I created a cross entropy loss. So this p theta came after applying the sigmoid in the last node. Okay. And that gives me variable between 0 and 1. So that was good for binary. But if I go to multi-class, in this case, let us say I have 4 classes, then these p, I should produce 4 of these p's. Okay, p1, p2, p3, p4. So how will I produce? So what is the extension of a sigmoid? Okay, so extension of a sigmoid is something called softmax. So softmax, I will define it. So for multi-class, extension of sigmoid, let us say, would be a natural extension would be, let us say, if I apply f soft max of x, then it will give me e to the x, let us say xi divided by sum of e to the x. So this is the softmax activation function. Again, you can see that, and I'm doing this for each of the components of xi. Okay. So let us say the values that I get until here are after the let us say the linear combinations that happens here. Okay. So let us say this is my node here, and then this linear combination happened, and this, after the linear combination, I got x1, and then further I have to do an activation of this. So I will apply a softmax on this. So f of, so let us say I produce x1, and then x2 again, like this one. This is our x2, this is our x1, let us say. And then after applying the softmax, and then again I will apply softmax and so on. So x3, x4, there are 4 of these. And once I have this x vector, I can take this as, so let us say I don't do activation yet, I collect this as a vector, let us say. So x1, x2, x3, x4, and then as a next step, I will apply the f softmax, and if I apply the f softmax, then it will be E of x1 and divided by sum of ej, okay, and then E of x2 divided by sum of ej, basically sum of these, and so on. Okay, so this will be my let us say this is what I'm calling it as p1, p2, p3, p4. Okay, so this, as you can see, this will be between 0 and 1. So because of this normalization, and these will be between 0 and 1. Each of these values will be between 0 and 1, because we are dividing the numerator by sum of the ej's. Okay, and this normalization essentially ensures that this becomes a probability distribution basically. So it's 0 and 1, and then if I sum over all of these, then it does sum to 1. So overall, it's a so then with this with these steps for multi-class classification problem, then now I will compare P1 with Y1, P2 with Y2, P3 with Y3, but then I will again use these cross entropy loss. But then only thing is that now I will do it over a sum of all the 4 outputs. In this case, I had only 1, so now I will have Y1, P1, 1 minus Y1 log P1 plus, and then basically average of the loss. Okay, so if I have to write down, then I have to write down this, then the loss function L p theta y will be sum of minus yi log of p, let's say theta I put above, it's a p theta I, and plus 1 minus yi, or minus 1 minus yi log of p theta I. So basically I have done I equals 1 to the number of classes, let us say k, and this becomes a loss function for the multi-class classification problem we have. Okay, so for an example of this, what we can do is we can create a, so for an example of this, let us say the P matrix that I produce, which is P1, P2, P3, P4, and this gives me output of 0. I think it should sum to 1, 7. Okay, so this seems to be the case. Okay, so let us say our P matrix is this, and then our Y matrix is Y is let us say 0, 1, 0, 0. So it's what I'm considering here is a multi-class but not multi-level. So there is also a extension where I may want to predict multiple objects in the same image. Okay, but here what I'm saying is like each image has only one. Okay, but then there could be 4 possibilities of possible. In this case, we had like cat, dog, horse, and so on. Okay, so we can also extend that to multi-level case, but then let us say in this case we have multi-class, but then the prediction that we do is for one of them, one of the k classes, let's say. So this is the Y we have, and this is the P matrix we have, and then we put it in the loss function there. So obviously, as you can see from there, I mean, it is doing component wise. So for one, it will be y will be 0 basically, yy is 0. Okay, and the probability of that, so this goes away anyway. So you're only looking into this log of pi p1 basically. So log of p1 is 0.2, and similarly you go to the second one, y2 is 1, so that guy becomes 0, so y2 is 1, and log of 0.7, and so on. So for this example, if I have to compute, then it will be so let us say the first one will be y0, so first one goes away, so this is like minus 1 minus y0, so this is 1 basically, and then log of p, first one is 0.2, p is log of, so this is 0.2, and then second one is 1 is remaining here, so this is log of 0.7, and the third one we go to the second term, so this is minus 1 log of 0.05, third one is also we go to the second one, this is 1 of log of 0.05. So this gives me the loss calculation for a given theta, obviously, right? So if the loss is high, then I will let the gradient descent minimize this. So I'm not going to the optimization method. You can look into this in the other course that I teach. So basically we have to do a minimization over this, but this is how the losses are calculated. Okay, So if my prediction was very good, then this would have been a very high number and others would have been very low number. Okay, so basically this term would have this term would have been only looked at basically, and then if this is like, let us say 0.9 or something, okay, let us say it's 0.99 or something, okay, and others are like very close to 0, then we are just looking into these terms and others just vanish, okay, because others just vanish because of the y itself. We don't even have to look at p. So other don't make any sense, just we look at this. So 1 minus 1 log of 0.99, which is close to 1. So basically log of 1 will be 0. So then your loss will be very close to 0. Then we will say that, okay, my model has learned, I don't have to do gradient descent to do further optimization update of theta. I will stop there, and then eventually I will declare that I have learned, my network has learned. Okay, and then for a new data I will start doing predictions on this. So this is so when we compute losses like this, then since these other values are, for the non-class values are 0, because I know, so you could have kind of just forgot, you could have forgotten these 3 anyway in the sum, right? So because they don't contribute anyway, so that's possible. You can just take the one that corresponds to the class that is present. In this case is the second class is present. Okay, so these are the basic ideas behind artificial neural networks. And then so a deep neural network computations can be written in a let us say written in terms of a for loop with some proper notations used. So I will do that now. So a feed forward, the forward pass in a neural network can be defined like this. So let us say I have these inputs, and then let us say I use the notation y0, or I can use let us say I redefine some notations here. So then here I have f1, f2, f3, f4, and then these are the connections we have. And so this is our input, obviously. Okay, this is the first hidden layer that I have drawn, and then let us say I draw a second hidden layer, and then these let us say the first layer activations all are f1. This is usually the case, and second layer is f2, and then I have these edges. It's a fully connected, so basically you're supposed to connect all the previous unit to all the forward units in the forward layer. So I'm not drawing all those connections right now. And then let us say I have fn minus 1, fn minus 2, fn minus 3, and fn minus n minus 1. All are n minus 1 basically. This is the last layer. And then we have some predictions. Let us say finally fn, and then this produces some output. Let us say yn. So in this case we are using the notation yn as our prediction basically, okay, not the level. So level could be denoted by some other later. So these are the connections we have. And so as we know, as a vector goes in and then it gets linear combination and activation and then so on. So basically we are trying to just describe this in a proper way. So let us say the values that do linear combination up to linear combination, we call this as z1. Okay, so this whole vector we call this as a z1, and then the output that we get we call this whole vector as y1, and then here again similarly we call this as z2, this we call this as y2, and similarly eventually we have yn. Okay, so this whole vector that we get just before f1 acts on those, this will be so this will be basically z11, this will be z12, this is z13, and so on, and then you will apply sigmoid on all these. Similarly the output that you will get will be scalar, so y11 will be the output from here, y12 will be the output from this, y13 will be the output from this, y14 will be the output from this. So you do this recursively. So all this can be written as a for loop. So in this case what we have taken is that there are n layers, capital N layers. So that's what we note down here, and then what we have assumed is that the width of these, so basically this we call it width of these layer. Okay, so width of layer So by width we mean number of hidden units in this layer. Okay, so in this case we have so we can call this as d1, okay, with the notation. So the width will be denoted by, let us say this is d1, this is d2, and dn. Okay, finally, so it is allowed to have variable number of width in each layer. Okay, you can increase or decrease this, and of course you can also have increase or decrease of number of layers. So all this we will use it to say if a vector x goes in, what are the operations that is applied and what is the final output. So this is what we are trying to do here, and these notations will help us write this. So if we look into this, then we can write the forward pass, and the forward pass, the input, we can have d vector and then the vector x that is going to be operated on. So we can call this j, and j equals 1 to d, and we set d0 equals to d. This is the width of 0th layer, and then we have so the way we have defined our notation. So y0 will represent the input vector. So we have y0 for all j is xj, and j equals 1 to d. So this d is the width of the input layer, which is this we call it d, okay, and then inner ones we call it d1, d2, d3. How many inputs units are there in this layer 2, how many units are there in layer 1, and so on. Okay, so d0 we just say d, which is the number of components of the vector x, and then we can so in our notations y0 was x, so y0 is basically x0. I mean yeah, so y0 will be our bias term basically. So bias term, as we said, we also include 1 as a bias term. Okay, so this y0 will be x0, which will be set, we will set it to be 1, which is the bias that we have, bias term we have. So then we can write an algorithm. So for layer k equal 1 to n, so n is the number of layers, and then within each layer I have these many calculations. So d, for loop for d as well. So for j equals 1 to dk, and then we have to compute these intermediate values, which is a linear combinations. So then this will be z j k is sum of I equal 0 to d k minus 1 w k ij, and then y I k minus 1, and then finally we have y k j, which is f k z k j. So this is the for loop we have, and so we have an input vector x, and then input vector x dimension is d, so hence we have a d-dimensional vector going in, and then we run this for loop for layers. So let us say we have n layers, and then within this each layer we have computations of these z1, z2, z11, z12, z13, and so on. So this is what we are computing here. We are taking a linear combination of the since yeah, we are taking linear combination of these these. So for y equals to yeah, for basically for layer 1, so we have to look into k equals to 1. Then for k equals to 1, this will be 0. So y0 was actually our input vector x itself. Okay, so this is what we say. Y superscript 0 was our input vector itself. So basically we are doing linear combination of our input vector with w0 are the weights of this. So the weights that go from here to here is w superscript 0, and this will be a matrix because 1 goes to many. So this will be the first row of your of the weight matrix, and then 2 goes to others. So 2 1, 2 2, 2 3, 2 4 will be the second row of your weight matrix, and so on. So this overall you will have a matrix of weights, and this matrix of weights multiply on the input to give you the output vector z, and this output vector z then is activated via f. So this is activation function. As I said, it could be sigmoid, ReLU, or so on. Okay. So this way you keep doing this. Then now this output is again done in the same way. These outputs that you have, in this case, the outputs after first loop will have the dimension d1 because there are d1 units. So each will produce d1 outputs. These d1 outputs will get linear combinations with the weight vector. So in this case, now if I go from here to here, then this will be weight matrix 1. Okay. Then k will become 1 here, and this will multiply with y1. So these are the y1s. It will multiply with the w1 will multiply with y1. Okay. So I mean w0 will multiply with k is, if k is 2, then it will be 2, right? So there is a little bit of, so w k1. So this we call it 1. Okay. And this we call it 1. So 1 applies on y0, 2 applies on y1, and so on. So this way we get the final output, okay, as y superscript n. And now it depends based on the problem at hand, whether I am doing binary classification, regression problem, depending on those, multi-class classification problem, depending on those, I will use let us say L2 loss, or binary cross entropy loss, or simple cross entropy loss, okay, summed over all the classes for multi-class. So these are the ways I can use a neural networks, the basic neural network, to do various learning tasks. So then there are variations on these. I'm not going into the training part of this, like how we will run the weights, because as you know, if you do gradient descent of the loss over the weights, this is a complicated function now. So training usually involves using gradient descent method, stochastic gradient descent method, and that requires computation of the gradients, and these gradients need to be computed with respect to the weights w. Okay. So how will you compute gradient of the loss with respect to w is looks a little bit tricky. And then for training, people use something called back propagation. Okay. So for training, use back propagation to compute the gradient with respect to the weights w, and then use stochastic SGD, stochastic gradient descent, to update the weights w. Okay. So these are kind of process we follow. We to use a stochastic gradient descent, I need the gradient computations, and this gradient computations is a bit tricky, and that is done via back propagation, which is a way to use a chain rule. So these things don't concern us for the moment, because for any arbitrary graph there are Python libraries that can do these back propagation automatically for us. We don't have to worry so much on this. We just have to explicitly mention what exactly is the graph for the neural network computation, and it will do the back propagation for us. So that's not necessary for us. Then there are many variations of neural network depending on the task we have at hand. Okay. So the type of problem we are trying to study is a so-called recurrent neural network. And recurrent neural network, basically we have started with autoregressive flow, and autoregressive flow is done for autoregressive process we started with, and that's for sequence data, time series data. So there is a concept of ordering, and then for those sequence type data, this type of network may not be suitable. Okay, because it's sequence data, so we have to put one input after the other, and then we may also have to relate the output to the next set of the inputs. Okay, so these are the things we need to kind of modify in our current artificial neural network to predict next set of sequences one after the other, and so on. Okay, so then there is network something called RNN, and RNN is something we will try to I will try to discuss in the next class. Okay, so with this I will stop.